a times sine of bx minus c plus d. Or the same thing with the cosine. So these are two familiar functions that we're discussing. And we already talked about 3 out of 4 letters in there. We know what A does, we know what B does, we know what D does. We kind of know what C is going to do as well. We just have to put it in a more scientific perspective. Okay, so just recall from Monday A, what does A do? Right, and we actually call A is the amplitude of that function, right? And we just look at the absolute value of A. Absolute value of A is the amplitude. If absolute value of A is greater than 1, then the graph stretches vertically. And if the absolute value of A is less than 1, then the graph shrinks vertically, right? So the sign of A doesn't matter as far as the amplitude is concerned. All the sign does, it just flips the curve of the x-axis. If A itself is negative, then the curve reflects over the x-axis. Okay? All right. What does B do? Right, it affects the period. In the sense that the period of the function is the absolute value of 2 pi over b. Then again, the sign of b does not matter as far as affecting the period of the function. If b is negative, all it's going to do is going to reflect the curve over the y-axis, right? How's that? Lovely. Now, we didn't talk about C. We talked about D. D is easy. What is D going to do? Yeah, moves it up and down, just like regular transformation. Nothing special going on. If D is positive, everything goes up. If D is negative, everything comes down, right? But on B, it should be clear. If B is greater than 1, then the period decreases, so the function shrinks. And if the B is less than 1, then the period increases, so the function stretches horizontally. Now D, those are vertical shifts. if D is positive, go up. If D is negative, go down. Okay? Now, C, we mentioned what C is going to do. So I'm going to write one of those functions here again. So A, let's just look at the sign. Sine of bx minus c plus d. So from our studies of functions, transformations, we understand that if you start subtracting or adding values inside the function, the graph is going to be shifting horizontally. So we call this the phase shift. So we need to figure out by exactly how much the graph is going to shift. And the way to do that is to rewrite these functions in this form. A sine of factor b out, and that leaves you with x minus c over b. So c over b will tell you by how far we're going to shift. And if you have a plus on the inside, we're going to go to the left. If you have a minus on the inside, we're going to go to the right. Okay? So c over b, so the absolute value of c over b is called the phase shift. Okay? So then it's all going to be depending on what sign you get inside the parentheses. If you have a minus, you go to the right. If you have a plus, you go to the left. Are you okay? All right. Good? Okay. So let me give you an example. I'll actually show you how to treat this whole phase shift slash period part in one smooth move. We're not going to have to really do much of this factoring and actually be shifting graphs. We can just figure out, we can cheat a little bit. But let me do an example. So given a function, (3x plus pi). Can you just, for fun, can you identify the amplitude? 2. Can you tell me what the period of this function going to be? 2 pi over 3, right? So the period is 2 pi over 3. What about the phase shift? Yes, pi over 3. You just take that number, this is the value of c, this is c, divided by that number, that's b. Just ignore the signs. So pi over 3, so the graph is going to shift by pi over 3. They're going to go to the left pi over 3 or to the right pi over 3? Left. Why left? Because it's positive. Okay? So we can actually sketch the graph. We can do the cosine with the period of 2 pi over 3. How do you do that? I mean, that's kind of a little, I mean, yeah. Yeah, you can do that. And then you also have to shift by pi over 3. So you're going to start from negative pi over 3, right? And then you're going to stop at just pi over 3. You go from negative pi over 3 to pi over 3, right? So that the period remains 2 pi over 3. So we can do it that way. There's another way to do that. But you're right, the most important thing is to figure out the first period, where it starts, where it ends, then you divide it into 2 equal parts, and you do the curve, okay? Now, we're playing with the cosine. So now we understand, hopefully, that in the regular function, you know, whatever, a sine x, the period here is just 2 pi, right? When it's just x, it's 2 pi, right? So that means the argument of the function is between 0 and 2 pi. That's 0 would be the first point of the period, and 2 pi would be the last point on that period, and then you get a sine curve from 0 to 2 pi. So whatever's on the inside, I can always put it between 0 and 2 pi. So for our function, which is, I almost forgot, 2 cosine 3x plus pi, right? The 3x plus pi has to be between 0 and 2 pi. That's the first period of a function. Just like before, whatever's on the inside is between 0 and 2 pi, gives you the first period of the function. Well, I can now solve for x. By solving for x, they'll actually literally tell me the interval of one of the periods. Well, so algebraically, if I solve for x, subtract pi all the way across, so it's negative pi 3x positive pi, and then divide by 3 all the way across. So it's negative pi over 3 positive pi over 3. So that's the first period of that function. So I can actually sketch that. Start at negative pi over 3. It will go through the origin, because that's the middle, right? And then just stretch it because of the 2. But basically what this gives me, that gives me those important points of the first period. So it's negative pi over 3, positive pi over 3, right? And it's a cosine curve. What does that mean? So it has x-intercepts here and here, and it will get stretched from 2 to negative 2 because of the amplitude. So then it has to start here. It will come down, right? Hit the x-intercept here. We'll go down here. We'll come up. Do that. So then you can copy paste the rest of that thing, right? So it's pi over 3. So the next one will be 4 pi over 3, right? So you have to do that. So you keep repeating that period. Did that trick make sense? You just put whatever's on the inside between 0 and 2 pi, and you solve that inequality for x. That automatically will take care of the phase shift, and it will take care of the period, just by doing that. You don't have to separately finding the shifting and then realizing what the period is. You're just figuring out what that initial interval of the period is. And it'll take care of that. We can do something like this. Y equals negative 2 sine of pi x. Do I really want to do that? No, I don't want to do that. Let's not do pi x yet. Let's do let's do 5x minus. Well, let's do minus pi. This would be a little messier. I can still answer all the questions as far as what is the amplitude, what is the period, and what is the phase shift. We can still answer those questions just by looking at the graph. I mean, by looking at the function. What is the period? I mean, what is the amplitude? 2. The only thing that negative does, it flips everything, but the amplitude is still 2. What is the period? 2 pi over 5. And what is the phase shift? Pi over 5. And where is it going to go, left or right? Right, because of the minus. It's going to be a little tricky to sketch, but we can interpret all of this by starting at pi over 5, positive pi over 5, and then draw a sine curve with 2 pi over 5 periods. So that's going to be a little hard to do. But if we try the same trick as we did in the previous example, all we know that the argument of this function, 5x minus pi, has to be between 0 and 2 pi. 0 to 2 pi, that's the initial period of a sine curve. And I'm just going to solve for x, right? So add pi all the way across. So this is pi, 5x, 3 pi, and then divide everything by 5. So that gives you pi over 5, x, 3 pi over 5. Okay? So we get the same information as before. We see that we started pi over 5, that means everything shifted, pi over 5 to the right, and the period is 2 pi, and the distance between this and that point is 2 pi. So we do get the same information. But at least that gives us the points. We can try to sketch the graph. So hypothetically speaking, this is pi over 5, whatever, right? So this is pi over 5, and then this is 2 pi over 5, this is 3 pi over 5, right? Just by the way the fractions work, right? So that means our function has an amplitude of 2 and a negative up front, so it will actually going to go down from here, and come back up, and come down. So that's that first period of sine. And then you just keep doing this, okay? Is that okay? So we'll actually, if I go back, it'll actually go through the origin again. Looks like it, right? And this is negative pi over 5. It will do that. Okay. This is negative 2 pi over 5. And of course, those peaks are going to be at pi over 10 and so forth, half distances. So we can just keep going like that. Okay? So let's just do a few more of this. And then this is just 5 pi over 5, which is pi. So it will do this again. Okay? So does this whole process make sense? How we can do those graphs? Now, if I added +1, we'll just have to shift everything 1 unit. Now, your x-intercepts would change dramatically, and we don't have tools to find those x-intercepts yet. Because you know, to find the x-intercept, you have to take the function, set it equal to 0, and then solve for x. So that means you have to solve a pretty messy trigonometric equation, which we don't know how to do yet. But eventually, we will be able to actually precisely find the x-intercepts. Okay? Now, your book, for whatever reason, which is beyond my understanding, does not ask you to graph functions of this form. Okay? And the way, and I think I mentioned that last time, the way we graph the cosecant and secant functions, we just ignore the fact that this is a cosecant. We think of this as sine. So first, graph y equals -2 sine of 5x minus pi. And we just did that. So I'm going to take this graph that we just copy. So remember how we graph the secant, or well, cosecant. Whenever this function intersects the x-axis, it will create a vertical asymptote. Remember that? Because again, when you think about the cosecant and the sines, they are reciprocals of each other. So when sine crosses the x-axis, my asymptote's a little bit slanted. Shouldn't be the case. Right? So the cosecant functions then define at those points. And now the rest, they'll always meet at those peaks. So the cosecant will be just a bunch of those little, not even parabolas, but kind of lookalikes. Well, because the parabola, you assume it just goes outward, while this one starts turning and basically flattening out. It does get, yeah, very close to that. Well, parabola is not. Parabola just keeps out, right? As x goes to, as y goes to infinity, x goes to infinity on a parabola. With this one's, as y goes to infinity, x goes to negative pi over 5. It slows down. So it doesn't satisfy the definition of parabola in our sense. Because we're going to define a parabola in a funky way eventually, hopefully, in this class, if we get to it. Because that's really easy. The way you graph those cosecants and secants, you first graph sine and cosine with the same exact amplitude and the shifts and all that. And then you just toast those little, you can call them parabolas, because they're parabola-looking things. Okay? Now, in the end of this section, the book goes into graphical addition, just very briefly. It's not that important, because if you ever need to graph functions of this complexity, you're probably going to use some kind of a graphing tool. But for example, what do we mean by that? If your function is defined by, let's say, well, I'll just do an example out of here. Yeah, 2 sine x plus sine of 2x. And the way you sketch sums of functions, because we will have no problem sketching 2 sine x, right? We understand that graph. That's just a sine stretched by 2. We're also not going to have any problems with sine of 2x. That's a sine curve with different period. What is the period of sine of 2x? Pi, right? So it's double the frequency of the original sines, we can say that. But then, so if you can sketch them separately, we can always add the heights of each function at any given point, and then you're going to get the sum of the two. So the way we do that, we will start with sketching both of these functions separately. So let's say if this is, let's say this is pi, this is 2 pi. Let's just do one period. So the first one, 2 sine x, is going to be something like that, right? So it's stretched by 2 vertically, while the other one has a smaller period. So the other one will be a normal sine curve, only doing this. It'll have 2 full periods between 0 and 2 pi. Okay? So then I'm literally going to add the values of those functions. What I mean by that is, let's say you take a height of one function and you add it to the value of another function. So I'm taking this distance and I'm putting it on top of one of the graphs. So that's a new point. So just taking this distance, you know, it's weird. I don't know how to do it without. Do you understand what I'm doing?
If you like drew the line and then moved it, and draw a line.
Yeah, I can do that. You're right. I can just, no, I can just put that. Well, yeah, I see what you're saying. So you mean like I can take this thing and just pick it up and then move it. So that's the new point over there. I can take this thing. Oops. I can take this thing and move it up. So that's the new point. I mean, it will be very hard for us to produce that graph. I mean, like here, I will actually take this line and I will be subtracting it from that. Does that make sense? Like this point will not affect anything. It'll just be back on that. So it will be like something like this. But, you know, when you ever faced with these types of graphs, with these types of functions, you want to use a graphing calculator, or we like this graphing tool. So we're just literally going to type 2 times sine of x plus sine of 2 times x. So it should give you something like that. Okay? I mean, ignore the parabola. So we'll still have the period and all that, but right. So you can model all your hard rates with that. You just have to come up. Yeah, you get amplitude, frequency, all them curvy things. You can just play by adding different functions. Okay. Another thing, and you should be able to do that by hand, at least visualize it. That's different. So that's when you add. Now the products are sometimes become important. So let's say, I'm just going to give you an example of what we mean. So let's say you have something like this. Let's say f of x equals, well, your book, I'm just going to do example out of the book and I'll do something else. Your book gives you this example. E to the negative x over 2 times sine x. Okay? So that's a product of two functions. So how we can graph it? It will come down to our understanding that no matter what, sine x is bounded by -1 and +1. That's just the way the sine works, right? That's the range of the sine curve, right? Between -1 and +1. Well, what I'm going to do now, I'll multiply all sides of this by e to the negative x over 2. The reason that I can just do that, because the exponential functions are always positive, so they don't mess with the inequalities. So I can do that. So this whole thing becomes negative e to the negative x over 2 less than or equal to e to the negative x over 2 sine x less than or equal to e to the negative x over 2, just e to the negative x over 2. Okay? So this is the function that was given to us originally, right? But you see, the thing is, I know how to graph negative e to the negative x over 2. I know how to graph positive e to the negative x over 2. I know the graphs of those two functions. They're both exponential. One is positive, one is negative. Okay? Now, the graph that we're worrying about is always going to be in between those two, right? But the sine is periodic, so you're just going to have some kind of a periodic nastiness stuck in between two exponential functions. Let me show you what it will look like. Because I will first graph the two exponential functions. So here's the e to the negative x over 2, so it does that, right? So this is e to the negative x over 2. Negative e to the x over 2 is just the same thing reflected. This is negative e to negative x over 2, right? Well, the rest is periodic. I mean, still, when x is 0, the sign is 0. So it will just keep doing something like that. So the graph that we actually talk about is that curvy thing that's stuck in between those two. It's always going to be bounded by those two graphs. But again, most of the time, we can just do this. So it's exponential of negative x over 2 times sine of x. So yeah. Oops, I deleted the wrong one. If I zoom out, see it does that? It'll come down, and it came down. Okay? I mean, it's just becoming astronomically huge at this point. Another example you'll see when you're actually going to take your calc courses. Another example is again, I just want to play with what the graph of this thing is going to look like. But again, I'm going to start with the same argument that no matter what x is, sine is between negative 1 and 1. No matter how hard it actually might be undefined when x equals 0, but I don't care about that for now. All I know that regardless of what x is, sine of 1 over x is still between negative 1 and 1. No matter how hard you try, the sign will not leave those bounds. Now, to produce my function, I'm just going to multiply everything by x squared. And we'll end up with a negative x squared less than or equal to x squared times sine of 1 over x less than or equal to positive x squared. So you just have a thing that you have a parabola that goes up, parabola that comes down. Well, the rest is going to be always in between those two parabolas. Okay? So I can actually sketch some version of this graph. You have positive x squared, and you have negative x squared. So our function is just going to be, it's not continuous at 0, it's undefined there, but it'll just do that. It'll just be between those. You just keep bouncing between those two parabolas. So you can kind of artificially create those functions like that. So you always use the fact that sine or cosine is between negative 1 and 1, and then you just multiply by what's missing.
We'll be able to figure out exact points.
Not really. Nobody cares about the exact points. You just want to see the exact shape. If I do this, x to the power 2 times sine of 1 over x, yeah. I see those graphs. You see, it does do that little. See, that's if I actually graph x squared and then I graph negative x squared. So you see, that's exactly what I'm talking about. It's just bouncing between those two. Okay, it's not turning around. Okay, I guess it's not. But it's just kind of really funky in there when you really zoom in. It just bounces between the two. Because like in Calc 1, they'll ask you a question like, what happens to this function right here as x gets closer and closer to 0? Because you're in trouble when x is at 0. Do you agree with that? When x equals 0, you're in big trouble because you're dividing by 0 in there. But what happens to the values of the function as x gets really, really close to 0? Well, you can just say, well, by looking at this graph, as we're moving closer and closer to 0, it's just being squished by those two parabolas. So the y values are very close to 0 as well. And actually, what you will call this process, you're literally going to call it the squeeze theorem. That you can squeeze a function into between some other two functions. That's what we're doing right now. Our function is squeezed between the other two. Okay? So that's going to be fun. All right, so that's the chapter 6. So there's some version of a homework posted that's due on Friday, actually. And we're going to start chapter 7. That's where we're going to have fun. Okay? So chapter 7 is dealing with trigonometric identities. And different formulas. You know a few already. We can use the unit circle to derive a few. We realize that on a unit circle, each point, x, y, is the same as saying cosine theta, sine theta. Right? We did mention that. On a unit circle, the x values are given by the cosines and the sine, and the y values are given by the sine. So right away, we have this one. Since tangent theta is y over x, by the definition, we can say that now the tangent theta is sine theta over cosine theta. So tangent is actually sine over cosine. I mean, that came up, but now we're making that knowledge official. Tangent theta is sine over cosine, while cotangent theta is the reciprocal, so that's cosine theta over sine theta. And also, we've mentioned that before, and I'm now just making this official, that secant theta is the reciprocal of cosine, so it's 1 over cosine. And cosecant theta is 1 over sine. Okay? So that's 1. So this will allow us to sometimes manipulate our expressions to turn everything in terms of tangents or cosecants and so forth. It will make, eventually we're going to be solving equations, we'll make solving equations easier. Now, on your exam, you had an extra credit question. Just by looking at the unit circle, can you identify whether sine, cosine, or tangent odd, even, or neither functions? Okay? Well, what is the definition of an even function? If you recall, it's the f of negative x equals f of x, right? So it doesn't matter whether input is positive or negative, the output stays the same, right? And the odd is right. So if you change the input, it will change the output. Okay? So if I just look at the unit circle, there's one way to make this argument. On the unit circle, for those sine and cosine functions, the input is theta, right? That's what the input of the function is. So if I talk about positive theta, that means we're circling this way. If I talk about negative theta, we're coming down, okay? So here's the negative theta, right? Well, now look, if I look at the positive theta or negative theta, the x value stays the same. Do you agree with that? The x values of these 2 points stay the same, right? The y values change, right? So which of those functions corresponds to the x value? I mean, it's written right there. Cosine. So that means right away that cosine of negative theta equals cosine theta. So cosine is an even function. Doesn't matter whether theta is positive or negative. Cosine is even. So this is a formula. We need to remember that. That cosine of a negative is the same as cosine of the positive. That doesn't matter. You can also make this judgment by thinking about the graph of the cosine. What do you know about graphs of even functions? Yeah, and that's the case with the cosine. Cosine is symmetric around the y-axis. Now, when we talk about the sine, you realize that when we change the sine of theta, the y value changed, right? Negative y, and the y corresponds to the sine. So you can say that sine of negative theta equals negative sine of theta. So sine is an odd function. Okay? But also, since tangent is y over x, since the sine of y changed, but the sine of x didn't, the y over x will still be negative in this case. So the sine of tangent also changes. So you can also say that tangent of negative theta is negative tangent of theta. So tangent is an odd function. Okay? So for the reciprocals, yeah. So the only even functions are cosines and secants. There's the only 2 that are even. The rest of them are odd. So sine odd, cosecant is odd, tangent is odd, cotangent is odd. Okay? And if you think about the graphs, cosine has a graph that's symmetric around the y-axis, so is cosecant. I mean, so was secant because it went up. But tangents are symmetric around the origin, and sines are symmetric around the origin, right? When you think about the graph of the sine curve, you know, it's this. It's symmetric around the origin. It's an odd function, therefore. So these are identities that you should know, the odd-even identity, because we'll be using that. The fact that sometimes when you end up with a negative on the inside of those functions, that negative can either disappear if it's inside of the cosine, or it can be factored out if it's inside of the sine function. Okay? But again, those come for free if you realize that, you know, cosine is even, sine is odd. Okay? All right. Any questions? All right. Well, the third one, which should have been the first one, this is the mother of them all. The big trig identity, the most important one. The Pythagorean identity. I'm not sure how to spell that. The big one. Okay? This is the one, it's one thing you remember after this class is this big identity. So, now let me ask you this question. I'm back on the unit circle. And if I look at this little triangle, by Pythagorean theorem, x squared plus y squared equals what? 1 squared, or 1, right? Hypotenuse squared. But since x is cosine and y is sine, I can conclude that sine squared, whatever, theta x, whatever you want to call it, plus cosine squared x equals 1. This is why we call it Pythagorean identity, because we use the Pythagorean theorem to come up with that. So this is the big one. Okay. And by the way, I never really mentioned this, but this is the notation, how we represent the powers of trig functions. We haven't seen that before, but we usually write it like this. Sine squared literally means sine of x squared. We just don't like to use the parentheses, so we're saying, the function is squared, which is not the same from saying sine of x squared like that. This is only the x that's being squared, while here the whole function is squared. So this is the notation for the square of a function. Okay. Now we can play with this identity. This little identity gives us many, many more. Like I can always solve for sine. Let's say sine squared x equals 1 minus cosine squared x. Right? And if I divide everything here by, let's say, let's divide everything by cosine squared. See what happens. Sine over cosine is tangent, so tangent squared x equals 1 over cosine is secant. So that's secant squared. Cosine squared over cosine squared is 1 minus 1. Okay, so that's another identity. You don't need to remember this identity, because it's, you just get it from the big one.
Why did it become a secant?
Because it's 1 over cosine, right? That's, yeah, because secant is 1 over cosine. Then, of course, this is the same as saying that secant squared x is tangent squared plus 1. Just algebraically solving for secant squared. So I could have taken the first identity and solved for cosine. I can say that cosine squared x equals 1 minus sine squared x. And then I can go ahead and divide both sides by sine squared. So that will give me cotangent squared, because cosine over sine is cotangent, right? Equals 1 over sine is cosecant, so that's cosecant squared x, minus sine squared over sine squared minus 1. And then, of course, I can manipulate that one. I can solve for cosecant. But again, all of those formulas are derived from the big one, sine squared plus cosine squared equals 1. This is the one that you need to remember. Like if you ask me what is cotangent squared is, I probably won't remember. I'll have to rederive it every time. Because to me, it's just easier to get the cotangent, just divide everything by sine squared. So you'll get 1 plus cotangent equals cosecant. So cotangent is cosecant minus 1. Cosecant squared minus 1. Okay? So this is what we're going to start with. These are some identities that you need to know. I mean, you need to know the basic ones, like tangent is sine over cosine. You need to know that. You need to know the odd even. They'll show up. And again, you need to know the big, the big one. The rest, this little ones are derived from the big one. This is the important one. You need to know the big one. So let's do a few examples where we simplify trig expressions. So here's an example. Cosine x times tangent x minus secant x. So I would simplify that, make it a little smaller maybe. Now, there is no right or wrong way of doing these problems. You just have to start doing them. Okay, whatever you think like you should do first will probably be okay. Okay, if I ask you to simplify this, you might end up with 6 different solutions, but they're all going to converge to the same place, hopefully. So what do you want to do first? Sure, nothing wrong with that. You can say that this is the same as cosine x. Now tangent is sine x over cosine x, while secant is 1 over cosine x. Absolutely nothing wrong with that. Your book does this example differently, but that doesn't matter. You're still going to get to the same place. Now what you want to do? Okay, distribute the cosine. Perfectly okay. You go times this, times that. So you're going to end up with cosine x times sine x over cosine x minus cosine x times 1 over cosine x. Absolutely nothing wrong with that. So I just don't want you to be scared, because you'll get scared of these problems. I don't want you to be scared of these problems. You just start somewhere, and you're going to get somewhere, okay? You might take a detour somewhere, but you'll get it. You'll get to the right place. As long as you just keep going without violating any major rules. Well, now think algebra. Can you simplify this? Yeah, I can reduce the cosines. I'm multiplying, dividing by cosine. I can reduce the cosines. So you'll get sine x minus 1. Done. Okay? Again, you might get 6 different solutions, but you're going to get to the same place. Okay? Now, the way your book did it, they distributed the cosine first, then they converted everything in terms of sine, cosine. They got to this point, then they reduced it. What you could have done, you could have said, well, same denominator, I can just combine this first, right? It's sine x minus 1 over cosine, and then you cancel cosines. You still get the same thing. So there's no right way of doing it. There are many wrong ways of doing it. You just don't, mess up your basic identities, but you should all arrive at sine x minus 1. Okay? So if I actually, for fun of it or whatever, if I actually graph sine x minus 1, we know the graph of that, right? It's a graph of the sine, just drop it 1, so it's just going to go below the x-axis. Well, if I graph that unholy mess, I'll get the same thing. Mostly. Because this one will have some domain restrictions because of the cosine, right? So it will be a sine curve dumped 1 unit with holes in it, where cosine is 0, so that's odd multiples of pi over 2. Okay, let me show you. If I actually type this in, if I just type in that, because I missed the graph before. Here the parabola. So yeah, that's expected, right? But if I type in, what was that? Cosine x, cosine x times tangent x minus cosine x. Secant, yes. Secant x. Oh, it didn't even do the holes. That's wrong. Should do the holes.
Would multiplying it by cosine not get rid of the holes?
Well, but I mean, again, the way we agreed that, you know, the domain of the function is just the way it's written before you start simplifying it. So technically, they should have holes. Okay, but it's okay. So it should have a hole here and a hole there at the peaks of the. But anyways, you get the same graph generally speaking. Okay. Well, that was fun. You're gonna have fun with this. These are fun. The trig equations and messing and blah blah blah. You have to be extremely good at algebra. I mean, it's not even funny how freely and comfortable you have to be with just basic algebraic factoring, fancy squaring formulas. Those shouldn't even be a thought in your head. You should go automatically recognizing the differences of squares and squaring things. And that's why I drove you crazy in 099 with that stuff. Because it has to just be, oh yeah. Don't even, so algebra should be like not an issue here, which will be an issue. Yeah. All right, let's simplify this one. What do you think like doing? Well, I cannot factor an x because the x is a part of the function. X is technically like that. It's not times x. That's a big thing. Sine of x, it's not sine times x, it's sine of x. So those are inseparable. But I can factor something. Other two expressions have something in common. Cosine, what is the power of cosine that I can factor? Yeah, I can actually pull out cosine squared x, right? Well, if I pull out the cosine squared x, what's left? Well, not yet, but sine squared plus cosine squared, right? Which equals 1. Sine squared plus cosine squared equals 1. So that's just cosine squared times 1, so that's just cosine squared. Lovely. I'm just going through examples. I'm in lazy mode. Oh, this is juicy. Questions on this? Is this okay? All right. Let's try this one. Simplify cotangent of negative theta over cosecant of negative theta. So what do you want to do?
Get everything into the 3 basic trig functions.
Okay, so cotangent, so if I write it properly, cotangent is cosine over sine, so this is cosine of negative theta over sine of negative theta, divided everything by 1 over sine of negative theta, right? That's kind of,
Is that how you do that with the negative theta on top and bottom? It doesn't.
it has to be everywhere. So the argument has to be the same. You could have dealt with the negative to begin with, but that's okay. So let me just rewrite it. This is the same as cosine of negative theta over sine of negative theta times the reciprocal, so that's sine of negative theta over 1. right? That's how you divide. You multiply by the reciprocal. So anything good happening? Cancel out of the signs. So you're left with a cosine over 1, which is just cosine of negative theta. You should also get rid of the negative, because cosine is an even function. The negative is just redundant, so it's just cosine theta because of the even function. Right? You could have just said right away, cotangent is odd, so I can pull out the negative. Cosecant is odd, so I can pull out the negative, so the negative just cancel right away. And then you just proceed with that. But this is okay. But yeah, if you start splitting them into different functions, whatever's inside the parentheses, it has to stay the same throughout your... So yeah, that works. Okay? Again, we can have 6 different solutions, all arriving at the same answer. So we use the fact that cosine is an even function here. So that's how the negative went away. Does that make sense? All right. Are you enjoying this? This is fun. This is algebraic trigonometry. That's what this is. No, it's algebra of trig. 2 sine squared t plus sine t minus 3 all over 1 minus cosine squared t minus sine t. So there's one other aspect of this problem. Sometimes you see like everything is sine, 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 except for one cosine, right? Sometimes it's beneficial to just convert everything in terms of sine, see what happens. And just based on what we wrote above, 1 minus cosine squared is sine squared. That's part of your big identity, right? One minus cosine squared is the same as sine squared, so we can always do that. So actually, we're very lucky here. Now, how about that numerator? What you have is you have 2 squared plus, just not squared, minus 3. So it looks like, yeah, this is just like, 2x squared plus x minus 3. Just think about factoring that polynomial. X is playing the role of sine right now. So we'll get used to this. We're just going to ignore the fact that it's sine. We just see that it's the same function. It's a 2 blah squared plus blah. So those are the same. Can you factor this? It's probably going to be 2x and x, right? You want to get negative 3 but positive in the middle. So you need 3 and 1. 1 is positive, 1 is negative. How do you put them? Probably the other way. Yeah, because you'll get 6 minus 1. So if you go the other way, if you go plus 3 minus 1, then you get 3x minus 2x. So you get x in the middle, right? So that means that numerator is factored into, instead of x, I can just put sine. So it's 2 sine t plus 3. And then it is sine t minus 1. So we just use basic algebraic factoring on that one. While in the denominator, it is sine squared minus sine. So I can also do some factoring in the denominator. Yeah, I can pull out a sine out of the denominator. So if I factor out the sine in the denominator, so it's sine t times sine t minus 1. By the way, do you see how very little knowledge of trigonometry we're using right now? The only place we actually used trig was here, when you replaced 1 minus cosine squared with sine squared. That's the only time where you actually used your knowledge of trigonometry. The rest is algebra, right? You're factoring. We can kill sine minus t. So we're left with 2 sine t plus 3 over sine t, right? So I can actually even go further. I can divide both of those by sine t. That becomes, well, let me just write it out slowly. 2 sine t over sine t plus 3 over sine t. Right, dividing both parts in the numerator. So the first one is just 2, while the second one is 3 cosecant t. Because it's sine in the denominator becomes cosecant. Isn't that fun? It's all right. Oh, I wish I had more. Let me pull up a few more. So, how would you go about that first one? I'm going to probably do it right here. Well, separately they are, right? So yeah, let's do the FOIL. So it's sine times secant. So let's just write it as sine x times 1 over cosine x. Is that okay? I'm converting them as I'm multiplying. Then it's sine times cosecant. So that's plus sine x times 1 over sine x plus cosecant times secant. So that's cosine x times 1 over cosine x. And then plus cosine x times cosecant. So it's 1 over sine x. Just FOIL, right? Well, the first one, it's sine over cosine. What is that? Tangent. So that's tangent x. Here you have sine over sine, that cancels, so that's 1. Plus cosine over cosine, that cancels. That's 1. So it's 1 plus 1, so it's plus 2. Right? And how about cosine over sine? Okay, so cotangent x. So that's about all we can do with that. Okay? How about next one?
Sine squared plus g sine cosine minus cosine squared?
No.
Minus.
The squares are positive, the middle is negative. So it will be sine squared, that's a Greek letter phi or phi, depending which your school of Greek was. So what do you want to call it, phi or phi? Let's call it phi. Okay. Because then you're inconsistent. Then we should call pi p. So that's what I mean by our Greek. We're going to pronounce letters. We're going to be breaking some rules. But yes, I'm okay with phi. So sine squared phi minus 2 sine phi cosine phi plus cosine squared phi. Okay? So what do you notice? Is there anything else you can do to simplify this?
Sine squared plus cosine.
Yeah, we see sine squared plus cosine squared, that's 1. So that becomes 1 minus 2 sine phi cosine phi. Okay? We haven't learned this yet, but actually, just a side note, 2 sine phi cosine phi is the same as sine of 2 phi, a double angle formulas. We don't know this yet, but eventually we'll be able to go even further. This will become 1 minus sine of 2 phi. But we don't know this yet. It's actually, it's still in that section. We'll get to this. Is that okay? How about 6? 1 plus tangent x quantity squared. So we can use the same formula, right? So that becomes 1 plus 2 tangent x plus tangent squared x. So every time you see tangent squared and you see 1, that should also trigger something. Do we have a formula that relates tangent squared and 1? Tangent squared plus 1 equals secant squared. Right? So I can replace tangent squared plus 1 with the secant squared. So this becomes secant squared x plus 2 tangent x. Okay? One minus sine t. I'm gonna skip 7. 7 looks weird. 1 plus sine t.
Maybe 7 sine squared plus. Oh, never mind.
Yeah, it's a little messy. I mean, we can do that one, but I don't want to. Let's do 8. 8 is simple. How do you do 8 really fast? Right, so it's difference of squares. So that's 1 squared minus sine squared t. So that's 1 minus sine squared t. Is 1 minus sine squared something special? Cosine. So 1 minus sine squared is cosine squared.
Why did you get the squares?
It's just using the algebra difference of squares formula. This is your a minus b. A plus b is a squared minus b squared, the difference of squares formula. So we're mostly using algebra in these problems. The trig is just kind of an afterthought. Okay? So we somewhat deviated from syllabus, the way we're covering these things now. I'm gonna have to update that. I'll give you a new syllabus. I mean, as far as the topics. Now, that might change the exam dates. So we'll talk about this, because right now your exam 2 is scheduled Wednesday after the spring break. So you go on a spring break, you come back, Monday review, Wednesday test.
What can we review on spring break?
Clearly. So we'll see whether that stays the same or we'll change that. I don't know. It's weird to have a test right after the spring break. Okay. Well, good. Lab.